Welcome to this explainer. Today we're diving straight into Einstein's absolute cosmic speed limit of space and time and uncovering the mind-bending physics that might actually let us cheat it. For over a century, we've known that 300,000 kilometers per second in a vacuum is the absolute unbreakable speed limit of our universe. It's literally hardwired into the fabric of reality. If you have mass, the universe simply looks at you and says, no. But today, we're going to explore a completely fascinating scientific loophole. Let's kick things off with a massive what-if. Whenever we think about faster-than-light travel, we usually imagine needing infinite energy to speed a massive spaceship up, right? Well, what if we took the exact opposite approach? Instead of trying to speed up to match the universe's ultimate limit, what if we just built a medium that slows light down to a literal crawl? I know, it sounds like pure science fiction, but it happens every single day. And it opens up this incredible doorway to moving faster than light without breaking a single law of relativity. Section 1. The light speed loophole, separating the absolute from the local. Okay, so let's clear up a major point of confusion right away. There are actually two completely different concepts when physicists talk about the speed of light. First, you have c. That's the universal constant, the unbreakable speed of information itself. You absolutely cannot go faster than c without violating causality and creating all sorts of messy time paradoxes. But then you have v, and v is entirely different. That's just a local speed limit. It's the velocity of light as it actually interacts with the atoms of a material medium. And the crazy thing is, that speed drops the very moment light starts bouncing through something like glass or water. And that brings us to a neat little formula for the refractive index, which we call n. It's super simple. N equals c divided by v. Here is the absolutely crucial takeaway. If you can move through a medium faster than c divided by its refractive index, you are successfully traveling faster than light in that medium. And guess what? That is completely legally permitted according to physics. Your speed is still way less than the absolute vacuum speed limit of c, but locally, you are absolutely outrunning light. Let's see just how extreme this gets in Section 2, slowing down light. From diamond to Bose-Einstein condensate. It is wild to see just how dramatically we can step on the brakes here. In a vacuum, light is cruising at maximum speed. Enter water, and it drops to about 225,000 kilometers per second. Natural materials like diamonds trap and slow light down to about 40% of its vacuum speed, which, by the way, is exactly what gives them that brilliant sparkle. But back in 1999, Dr. Lena Howe's team at Harvard used a Bose-Einstein condensate to do something truly shocking. Get this, by firing a laser into a supercooled cloud of sodium atoms, they manipulated the quantum states and achieved an unimaginably massive refractive index. They slowed a pulse of light down to just 17 meters per second. That is barely 38 miles per hour. They brought light down to an everyday human speed, a speed where you could literally outrun a photon on a bicycle. No way, right? But hold your horses before you try to sprint past a beam of light. Section 3. The danger of Cherenkov radiation. The subatomic speed trap. You've definitely heard of a sonic boom, right? An aircraft breaks the sound barrier, outruns its own pressure waves, and they pile up into a massive acoustic shockwave. Well, Cherenkov radiation is the exact same thing, but for lights. When a charged particle breaks the local light barrier in a medium, it outruns its own electromagnetic polarization. The light waves just can't get out of the way fast enough, and they create this blazing blue shockwave of lights. It's exactly why nuclear reactors submerged in water have that eerie, glowing blue halo. Now, you might be thinking, hey, I'm not a subatomic particle. I don't have a net electric charge. Well, actually, your body is a walking saltwater solution filled with dissolved charged ions like sodium and potassium. Because you're made of protons and dissolved ions, moving superluminally means you would generate your very own lethal dose of Cherenkov radiation. You would emit a continuous shockwave of intense ultraviolet light and X-rays. It would instantly tear apart your DNA, all while you essentially cook from the intense electromagnetic drag. So yeah, not a fun way to go. Clearly, we can't just go running through water or gas at superluminal speeds. Let's move to Section 4, Engineering the Ultimate Medium, the virtual laboratory. To actually survive this, we're going to have to engineer a completely hypothetical metamaterial from scratch to bypass all these physical threats. Let's build this together, property by property. First up, we need an ultra-high refractive index of exactly 1 million. Why? Because that drops the speed of light to 300 meters per second, which is roughly 670 miles per hour, just a hair below the speed of sound in our atmosphere. That's a speed a highly advanced vehicle could realistically achieve. Next up, we have to solve mechanical drag. If you tried hitting 300 meters per second in a normal fluid, atmospheric drag would literally vaporize you. Poof! Because drag increases with the square of your velocity. This is exactly why our medium absolutely must be a quantum superfluid. A quantum superfluid has zero internal friction. None. It would allow a ship to glide right through it with absolutely zero mechanical drag, giving a silent, completely frictionless passage. But, and there's always a but, there's a major catch with superfluids. You can't just move at any arbitrary speed. We have to make sure the land-out critical velocity of our fluid is strictly higher than the local speed of light. If we exceed that land-out critical velocity, all our kinetic energy would shatter the quantum coherence. It would generate quasi-particles and instantly restore all that lethal drag. So VL must be greater than C divided by N. And finally, to stop ourselves from glowing to death from that Cherenkov radiation we talked about, we have to engineer what's known as a photonic bandgap. Think of this like a microscopic, periodic structure in our metamaterial that completely forbids light of specific frequencies from even existing. By physically deleting the available quantum states for ultraviolet and blue light, the emission process is just completely shut down. We effectively silence that deadly electromagnetic shockwave forever. All right, the math checks out. Section 5, Experiencing Superluminal Travel, Walking Through the Mirror. We've designed the perfect medium in our lab. But what would it actually look and feel like to cross the local light barrier inside it? Picture this. You're accelerating in a maglev pod through a tunnel filled with this glowing violet superfluid. Because we engineered it with zero friction, there's no engine roar, no vibration, no heat. Just absolute silence as the speedometer steadily climbs up to 299 meters per second. At precisely 300 meters per second, things get really weird. The light from your own headlights can't escape ahead of you, creating this blazing wall of frozen photons stacked right on the nose of your ship. And the exact moment you cross that barrier, boom, you plunge into absolute pitch-black darkness ahead. You are literally outrunning your own headlights and all future visual information. Out the side windows, it gets even crazier. You'd watch the universe play in reverse as you catch up to light waves that were emitted in the past. Even the Doppler effect would entirely flip, redshifting everything ahead of you. It would be an incredibly surreal, dreamlike landscape. That is a serious trip, and it proves we can outrun light in a medium. But let's take it one step further. Section 6, Breaking the Ultimate Limit, the Vacuum Loophole. Let's see how this builds up to challenging the universe itself. So here's a massive thought for you. What if the speed we call c, the absolute limit of the cosmos, is actually already slowed down? Quantum field theory tells us that a perfect vacuum isn't just empty nothingness. It's actually a boiling soup of quantum fluctuations and virtual particles just popping in and out of existence constantly. And any photon traveling through space has to interact with these virtual particles, slightly delaying its progress. Which begs the question, if space itself is essentially a medium, can we engineer it to make light go faster than c? Mathematically, the answer is actually yes. Back in 1990, a physicist named Klaus Scharnhorst proved that if you place two conductive plates incredibly close together, you physically restrict the wavelengths of virtual particles that can even exist between them. You essentially thin out this quantum soup. And doing that pushes the effective refractive index of the vacuum below 1.0, meaning light can travel faster there than it does in a normal vacuum. Now, okay, don't pack your bags for Alpha Centauri just yet. The speed boost from this is agonizingly tiny. We're talking 1 part in 10 to the 36th power. That is a decimal point, followed by 35 zeros and a 1. Not exactly warp drive. Plus, the microscopic gap between those plates couldn't even fit a single atom, let alone a whole spaceship. But as a concept, the Scharnhorst effect is a profound revelation. It tells us that the cosmic speed limit of the universe is deeply tied to the quantum state of the vacuum itself, and it leaves us with this final, staggering question to chew on. If a highly advanced civilization could one day manipulate the quantum vacuum on a massive, macroscopic scale, could they essentially thin out the fabric of space-time itself to travel faster than c, bending the absolute speed limit of the cosmos without ever actually breaking the core laws of relativity? The physics says it's totally possible. It all just depends on how good we get at engineering the ultimate loophole.
Please like and subscribe.